So I'm going to go over the chapter 10 review questions. I'm not going to go over the first question because it just answers like definitions and key terms, and so you can do that on your own. Question number 2 says, what is a Pascal? And if you'll remember, a Pascal is one of the many ways that we measure pressure, and it's actually our standard unit for pressure that we're going to be using. Question number 3 asks, what is a barometer? I've tried to draw one. I am not an artist, but essentially you would have a closed glass tube, and this would be mercury, so it would have been a silver liquid. And as air pressure pushed down on the mercury, it actually then would push it up the tube, and that's a barometer. It's just a device used to measure air pressure. Then number 4 says, why are inches of mercury or millimeters of mercury used as a unit of pressure? And this comes from this barometer. You actually would have used a ruler, and it would have had marks on it like a ruler that would have gone up the tube, and you would have basically counted how many millimeters of mercury that it would have gone up. And so at 1 atmosphere, it would have gone up 760 millimeters. And so that is why we measure millimeters of mercury. Right, question number 5 says that if you put an inflated balloon into a container and then you add a lot of pressure to the container without changing the temperature, what will happen to the size of the balloon? And so you can just envision if you have a balloon and you were to put a lot of pressure on the outside of this balloon and we're not changing the temperature at all, the balloon is actually going to decrease in size. And so you could kind of see this if you take the combined gas law, and we're going to not look at the temperature because in temperature in this case does not change. And so if I need each side to stay the same, I'm just going to put in some numbers to kind of try to show you what would happen. So let's just say our volume is 1 liter and our pressure is 1 atmosphere. And so it equals 1. And in our second situation where we increase the pressure, let's put in a 2 for the pressure, and let's say we don't know what V is. Well, if I were to work this through and solve, so I would say 1 equals divide by 2. So the volume would actually have to become half. So as you increase the pressure on the outside, the volume is going to be decreasing. Question number 6 says if you inflate a balloon at room temperature, so let's say this balloon that I've just blown up, and then I was going to go put it in my freezer, and pressures are not going to change, what will happen to the size of the balloon? And so I know that when molecules get cold, they slow down a bit and they will start to get a little bit closer together. And so the gas particles in this balloon will quit moving around as much and pull closer together. And so the volume will actually get smaller. And you can do this easily at home. Just blow up a balloon, go put it in the freezer and come back in a few hours and you will see the balloon get smaller. So question 7 is just referring to the Kelvin scale, and it asks you, what is an absolute zero? Like, what does it mean for an absolute zero? And if you'll remember on that Kelvin scale, we've talked about how that is when molecules stop moving at all and they have no energy in them. And that would be an absolute zero. They would have absolutely zero movement, temperature in the molecules. And that is not possible. And so I guess the answer to question number 7 would mean like an absolute zero is not possible. Question number 8 tells us what is the boiling point of water at 1 atmosphere. And so I know that water at 1 atmosphere boils at 100 degrees Celsius. So I'm going to do that basic conversion from 100 degrees Celsius into kelvins. Now, the reason we say at 1 atmosphere is if you'll remember the chart from the end of the chapter, depending on your atmosphere affects your pressure, and that affects the temperature at which the water goes from a liquid to a gas. So this one is at 1 atmosphere. So 100 degrees Celsius, and we're going to convert that to kelvins. And so you just take your Celsius and you add 273.15. So my Celsius in here is 100. So the kelvins temperature is 373.15. Question number 9 tells us that nitrogen condenses at 77 degrees or 77 Kelvin. Condenses means it goes from being a gas into a liquid, and it's wanting us to know what's that temperature in Celsius. So we're going almost the opposite of what we were just doing in the previous problem. So I have my kelvins. I know that equals Celsius plus 273 plus 0.15. And so I'm going to just subtract 273.15. And I get negative 196. And I know, Miss Holly, what happened to that decimal, right? But when we're doing significant figures and we're doing them in measurements, we're going to measure it to the least precise number we were given. And so 77 in this measurement, we're actually not giving any decimals. We're only given to the ones place. And so we're going to therefore report our answer to the ones place. So for question number 10, it says if we're extrapolating information off of a graph, a good scientist keeps the range of extrapolation, and you're looking for either small or large, compared to the range over which the data has been measured. I'm trying to draw you a rough graph for this, but let's say we have a graph and it looks something like this, and we are doing something over time, and you're actually going to start seeing a correlation come up. Now, you would not, I don't know if you can even see my dots. If I'm going to draw a line from this, any line that I'm drawing past this is an extrapolation. And so I wouldn't want to extrapolate from data way out here, because that data could have a large % error to it. So I'm going to want to extrapolate a pretty small range compared to the data that I've measured. So I'm going to actually only want to extrapolate a smaller amount than the data that I've measured, so I can only safely extrapolate just a little bit more. So for question number 11, I'm not going to write it down, but it asks why must we use the absolute temperature scale or the Kelvin scale when we're dealing with gas laws? So that comes from this equation. If you'll notice, you're dividing by T. And if we were using Fahrenheit or we were using Celsius, you can actually have a temperature of 0 in those scales. And so from algebra, you should know that you actually cannot divide a number by 0. It's not possible. And so if we use the Kelvin scale, where obtaining 0 is not possible, we will never have to worry about dividing by 0. Number 12 tells us a piston, so a piston, so that would be located in an engine, contains 45.6 milliliters of gas at a pressure of 815 torrs. And then it tells me that the temperature is going to stay constant. So it says temperature does not change. What is the volume of the gas at a pressure of 760 torrs? So for this question, you first have to ask yourself, am I using the ideal gas law or am I going to be using the combined gas law? And we're actually taking a piston with gas in it, and we're taking that same piston and we're just changing the pressure to it. So since I have one vessel or one scenario and I'm just changing part of it, I'm going to be using the combined gas law. So if we have our combined gas law and the temperature stays constant, I'm not going to use the temperature part of the gas law. I'm just going to be using the P1V1, P2V2. So P1 and so I know that the initial pressure is 814 torrs. It's okay to use torrs, I just have to make sure that I use torrs on the other half of the problem too. And I know that the volume is in 45.6 milliliters. And so I'm just going to set that equal to the second part, the second scenario of the piston. And this is where the pressure changes to 760. And then volume, or V2, is what I'm looking for. I don't know what that is. And so we're just going to solve this through. You would do 814 times 45.6. You can leave this in milliliters. You don't have to convert it to liters, just if you leave it in milliliters. Now, don't get that confused with the ideal gas law, this one that you have to use liters on. If you multiply these together and then divide by 760, and I would recommend putting it in your calculator and one fell swoop, that way you don't make it, like that way you round the least amount of times, you're gonna get V2 is equal to 48.8, and remember we used milliliters, so the volume is going to be in milliliters. So just as a recap of this, basically we have a piston of gas and its initial pressure. We know its initial pressure and we know its initial volume, and we're going to be taking that and we're actually going to be changing the pressure. I'm lowering the pressure from 814 to 760, and so the volume is actually going up from 45 to 48.8. Problem number 13 tells me a flexible container, just kind of like a balloon, is held at a constant pressure, and it starts with 1.2 liters at 25 degrees Celsius, and its volume, what happens to its volume at 50 degrees Celsius? So I have my balloon here, and I'm basically changing its temperature from 25 degrees Celsius to 50 degrees Celsius. Since it tells me it's at a constant pressure, I can actually take my combined gas law and take the P out. So I'm just going to use V1 over T1 equals V2 over T2. Now, if you'll remember, this is a gas, and so we have to use kelvins. That way we don't put ourselves in the position of dividing by zeros. And so we first have to convert 25 degrees Celsius and 50 degrees Celsius into kelvins. So stop, take a minute, go ahead and convert these two into kelvins, and then just double check yourself. All right, so when I converted these into kelvins, I don't want you to get totally confused with my significant figures here, but just like we talked about last time, I'm basically taking 50 degrees and I'm adding 273.15. And if you'll see here, I don't have a 0.15 in my answer. I actually rounded that to 0.2. And the reason I did that is in the problem, it tells me to the 10th of a degree. And when I'm doing significant figures with measurements and I'm adding or subtracting the figure, I do it to the least precise. And so the least precise has a 10th. And so my answer then is only going to have a 10th. This is from like the first chapter if you're kind of confused on it. But this is my 50 degrees becomes 323.2 kelvins, and 25 degrees becomes 298.2 kelvins. So now I can go in and I can put these into the combined gas law. Since I'm using the combined gas law, pressure is constant, I'm just going to be using V1 over T1 is V2 over T2. So you're just going to take that information and you're going to plug it in from the problem. So I am starting at 1.2 liters, so that is V1. And the first temperature is 25 degrees Celsius, which I've converted to 298.2 kelvins. Sorry, all my markers are dying today. And I don't know V2, that's what I'm looking for, but I do know the T2. I erased it. So you would end up with, I'm running out of space, every marker today. Every marker. All right, so you would end up with a V2 and you would get 1.3 liters. How did I do that? I did 298.2 K times V2, and then I would set that equal to 1.2 times 323.2. And this is a volume, and we put the volumes in liters, so my answer is going to be in liters. All right, question number 14, I'm not going to write the whole question out. It's kind of long, but I'll get the gist. So in this problem, we have a helium balloon, and they give me all the information about its current status as it's up in the air. So they tell me it has a volume of 35.4 liters. It has a temperature of 0 degrees Celsius, and that it has a pressure of 0.619 atmospheres. So that helium balloon's up in the air and it's coming down. And so as it comes down, its volume is actually decreasing to 21.1 liters. And if you think about it, it makes sense because as it gets closer to Earth, there is more pressure outside of it pushing into the balloon, so the volume is going to decrease. The temperature is getting warmer. It's going to 22.9 degrees Celsius, and its pressure is what we're looking for. So we're going to use this combined gas law because I've got one balloon and I'm changing its scenario. It's going from being up in the air down to ground level. And so since I've got the one balloon, I'm just changing its situation. I'm going to use the combined gas law. Remember, you cannot use Celsius. So of course they give it to you in Celsius, so you're going to have to convert these temperatures. Now this one is really easy. I'm just going to add 273.15. I've gone through now and I've fixed my temperatures. Actually, so for this one, as you convert to kelvins, you're going to keep the hundredths decimal place, because when they give you the temperature, they don't just tell you it's 0 degrees Celsius. They actually tell you it's 0.00 degrees Celsius. And when they give you this temperature too, they give you 2 decimal points afterwards. And so we're going to keep the 0.15 for this problem. So this equals, I end up with 0 degrees, so I just add 273.15. So I get 273.15 kelvins. That's nice and easy math. Then when I add 22.9 to 273.15, you get 296.05. And like I always ask you to do with these problems, try and figure it out yourself. So then pause it, come back and check your work. So the next step, we're basically just going to take all this information and we're going to put it into the combined gas law. So we're going to say P So when you put this into the combined gas law, this is what you get. You get pressure of the first scenario, P1 is 0.619 times the volume, which is 35.4. We're going to leave it as liters, and divide that by the temperature. You're going to then set that equal to P2, and the reason we don't have a number here is because this is what we're looking for. And then we're going to times that by our volume, which is 21.1 liters, and we're going to divide it by our temperature in kelvins over here, which is 296.05. So go ahead, stop, do the math, and then come back and check yourself. All right, I get the pressure is equal to 1.13, and in this problem, pressure is in atmosphere, so this is in atmospheres. Now, if you have all these steps right and you are getting a different answer, go back and double check how you're putting in your calculator. Check to see if you're using parentheses if they're needed and those things. Question number 15, there's 3 parts to 15, and each of the parts gives us 2 scenarios. And it asks you which situation is most likely to produce a gas that's like ideal. And so quick few notes, remember if a gas is ideal is it will have a low pressure. It will have a high temperature. And if it has a low pressure and high temperature, it will take up a lot of volume. And so we're going to look at these scenarios and just analyze them to see which one of these are going to behave most ideally. So for part A, these are the 2 scenarios. So I have a temperature of 124 kelvins and I have a pressure of 1 atmosphere. And for this one, I have a temperature of 280 kelvins and 1 atmosphere. So the pressures are the same, so I'm going to compare the temperatures, and an ideal gas is at a higher temperature. This one is at the higher temperature, so this is going to behave most ideally. For part B, we're given temperatures are the same. Both of these gases have a temperature of 275 kelvins and 275 kelvins. But what is changing is the pressure. So for this one, the pressure is at 700. And for the next one, the pressure is actually really high. It's at 4,567. And those are both units are in torrs, so we can just compare the 2. And remember, for an ideal gas law, we want low pressure. So the one at the lowest pressure is this one. For letter C, we get the first part is one that's at standard temperature and pressure, and then we have one that is at 100 kelvins and 15 atmosphere. So STP, as this is at 0 degrees Celsius and at 1 atmosphere. So since 0 degrees Celsius is 273 kelvins, which is actually a higher temperature and a lower pressure, this one is going to be your most ideal gas. Number 16, ask how many moles of nitrogen are present in an 891 milliliter container at 23 degrees Celsius and 345 torr. Well, I am not using one gas at one situation and changing it. So I'm not going to be using the combined gas law for this. I don't have P1 and P2 and all that part. But there is a hint to this problem that tells me which equation I'm using, and that is how many moles. So if you'll remember, when we have our ideal gas law, we actually have a variable for moles in this, and so we're going to be using the ideal gas law. Now, this problem gets a little bit tricky because they ask you to do a lot of conversions. So if I'm using the ideal gas law, and I know my constant for R has liters and atmospheres, I know that then that when I put in volume, I have to put it in liters. I didn't give it to me in liters. And I also know that I have to put this in atmospheres. So first you have to do those conversions. So if I have 345 torrs, I'm going to use the factor label method, and I'm going to atmospheres. And if you'll remember, 760 torrs is 1 atmosphere. So I'm going to put 760 on the bottom and 1 atmosphere on the top. Just going to do 345 divided by 760, and I get 0.454 atmospheres. Now I'm going to also so I'm going to use this information. The other thing that I'm going to do is I'm going to take 891 milliliters, and I'm going to move my decimal 3 places to the left to get it into liters. 1, 2, 3, and this is in liters. And I did that really fast, but if you need to go back and do the factor label method to get there, or King Herod died, feel free to stop and check it to make sure you do that correctly. So there's one other conversion, and that is that when we're using this, it's a gas law, so we have to have our temperatures in kelvins, and it would be way too easy if they gave it to us in kelvins. So I'm going to take 23.0 degrees Celsius and convert it to kelvins. So to do that, you just take 23.0, you add 273.15. Now, when I do this, I'm actually going to only be producing my answer with 1/10 of a decimal in the answer, and so that's why it's rounded 0.15 to 2, and we've talked about that in all the past problems as to why I've done that. So you're going to take all this information, and we're going to use PV equals nRT. So I'm going to start right here. I'm just going to write the formula. Make sure I have everything in the right units. So my pressures, I have to have it since in atmospheres, which I have. All right, so I'm going to put my pressure. It has to be an atmosphere. I'm actually going to keep all my units in this math and show you how they cancel out, even though I don't always do that. I guess a good teacher would keep her units all the time. N, I don't know. R, if you don't know it, you have it written down on your note card, I hope. And temperature we found to be 200.2 kelvins. So I'm actually going to rework this problem to solve for N. So what you're going to end up doing is dividing by all of this on that side, and then you would divide by all of that on this side. and that would be equal to N. Go ahead and put in your calculator in one big motion. Just make sure you're keeping your parentheses on everything in the top and your parentheses around everything in the bottom. And when you do that, this Kelvin will actually cancel out with this Kelvin, and this liter will cancel this out. Atmospheres will cancel out, and the only unit you'll be left with is moles, which is actually what you're looking for. So it's a good way of checking yourself. So you end up with 0.166 moles, and this is 0.166 moles of nitrogen gas, if you even remember where we started with this problem. Number 17, getting a little lazy writing it shorthand, but it asks what is the volume of 10 grams of water vapor at 134.5 degrees Celsius and a pressure of 567 torrs. So this is another ideal gas law equation, and you just have to make sure that you have everything into it. So except for this time, I'm not solving for my moles, I'm solving for my volume. So they give me a pressure, I just have to do some conversions. They do not give me the volume. They do not give me the number of moles, but y'all are really good at stoichiometry at this point, and you can convert grams to moles. We know R and we know T. So we're gonna first start with all our conversions. So let's convert water to moles. Go ahead and try it yourself. So if I'm doing grams to moles of water, I've got 10 grams of water, and I'm gonna multiply it by the molar mass, which these are the numbers you get from your periodic table. So if you look on your periodic table, you have hydrogen, it is 1.01 grams, so you've got 2 of those, and 1 oxygen, which is 16. So 16 plus 1.01 plus 1.01 equals 18.02. And if I put it on the bottom, grams cancels out, and I'm left with my answer in moles. And you get 0.555 moles. And the reason we have 3 numbers in our answer is because we're multiplying or dividing with significant digits. We actually use the least amount of significant digits given. So for this one, they gave us 10.0, so we have 1, 2, 3 significant figures. Even though there's 1, 2, 3, 4 in this one, we're gonna use the least amount, which is 3. All right, the next thing I'm gonna convert is, let's convert the temperature of Celsius to Kelvin. So you're just gonna take that and you're gonna add 273.15. You get 296.2 kelvins. I'm reporting that to the 10th of the degree because I started with a 10th of a degree in Celsius. The next thing I'm gonna convert is going to be pressure. I'm gonna take 567 torrs. I've got to put it in the atmosphere. So then I'm going to put 760 torrs on the bottom, so it cancels out. So you end up with 567 divided by 760, and you're left with 0.746 atmosphere. So I think I have everything that I need right now. I have pressure, right? I'm looking for volume. I have my number of moles, R is a constant, and I know temperature. So let's go ahead and we're gonna put all that in to PV equals nRT. So when you put this in for PV equals nRT, you get 0.746 times V, and it equals 0.55 times 0.0821, which is your R, times your temperature. So I would move this pressure over here, and I would put this all in my calculator in one step to try to limit down your rounding errors. Just make sure that everything above the line is in parentheses and everything below the line is parentheses, and you get a volume of 24.9 liters. So for problem number 18, we're given a decomposition equation. So you have, remember, a decomposition equation is when you take one compound and you break it up into its parts. And so for this one, we have potassium chlorate. We're actually breaking it up into potassium chloride and oxygen. And this problem tells me I have 150 grams of this that I'm starting with. And it wants to know what's the volume of oxygen made and it tells me that it's at STP. So this is actually going to be an ideal gas law equation, but it does get a little bit tricky when you're looking at it because the information they first give you is potassium chlorate, and you have to have information to put in for oxygen. So one of the things we're going to calculate is moles of oxygen, because you need moles for the ideal gas law. So go ahead and stop and see if you remember how to go from grams of potassium chlorate, you're going to go to moles of potassium chlorate, to moles of oxygen, and that's what we're looking for. So first we're going to go from grams to moles, and so I have 150 grams of potassium chlorate, and if I add up all the molar masses from my periodic table, I get 122.55. So you're going to take 150, you're going to divide it by 122, grams is going to cancel out, and you're going to be left with moles, and your moles are that's moles of KClO3. Now remember, I'm actually not wanting moles of this guy, I'm wanting moles of this. So if you'll use your coefficients from your balanced chemical equation, we're going to put moles of KClO3 on the bottom, and we're going to put moles of oxygen on the top, and we're going to be left with our answer in moles of oxygen. And you get you should get 1.836 moles of oxygen. So just what I did is I took grams of KClO3, multiplied it by its molar mass, or divided it by its molar mass, and I got moles of KClO3, and then I used my balanced chemical equation and the coefficients of 2 to 3 to go from moles of this to moles of oxygen. So now I know moles of oxygen. I'm going to actually erase so that I have space for the next part. Now I'm going to actually just take all this data and start putting it into my ideal gas law, which is PV equals nRT. And try to remember, in this problem, we're actually solving it for the oxygen. It tells me that it's at STP, so STP pressure is just 1 atmosphere. I am looking for my volume. I have calculated my moles. I know my R. And then I also know that at STP temperature is given to me as 0 degrees Celsius, so I can very quickly add that and make it 273.15 kelvins. So this is a nice one because this is times 1, so you're gonna end up with this number, and you're going to multiply these 3 numbers through. And you should get 41.2 liters of oxygen. So basically, if you were to start with 150 grams of potassium chlorate, you would actually end up with, in the end, 41.2 liters of oxygen. So number 19, we're actually going to switch from ideal gas law and use Avogadro's law. So for number 19, it gives us an equation of burning propane. And if you'll remember, a combustion reaction is when you take a hydrocarbon, you burn it with oxygen, and you produce carbon dioxide and water. It tells us in this equation that you take 567 liters of propane, and when I'm burning it, my question then asks me how many liters of oxygen, or how many liters of carbon dioxide are made. And it tells me that it's done at 1.04 atmospheres and 1,995 degrees Celsius. And so this problem is I can use Avogadro's law, because with Avogadro's law, I know that if the temperature and the pressure stays the same throughout, I can actually take these coefficients and use them as my volumes. And so that is why in this problem, they tell you the pressure and the temperature so you can decide that it's staying the same throughout the problem. And so we're just basically going to take this and use our coefficients to convert. So what I mean by that is you're going to take 567 liters C3H8. And I can use these numbers. So I'm going to use, I think I misspoke earlier and said we were looking for oxygen. We're actually looking for liters of CO2. I'm trying to make it through it without all my markers dying today. Okay, but since I know that the temperature and pressure stays the same, I can actually use the coefficients to calculate the volume. So I'm just going to say I'm starting with 567 liters of this propane, and I am going to put the coefficient of propane on the bottom, which that's an 8, which is a 1 here. Put the 1 here, and I'm going to, so that can cancel out. And I put a 3 on top because there's a 3 in front of the carbon dioxide. And so you're just going to take 567 and multiply it by 3, and that's going to give you your liter. So you get 1.7 times 10 to the third, or 1,700 liters. So question number 20 is a partial pressures question, and we're going to use Dalton's law of partial pressures. But the question tells you that a balloon is filled with 345 torrs of oxygen gas and 416 torrs of nitrogen gas, and it asks you to calculate the mole fraction of each gas. And so before you can figure out the fraction of the gas or the pressures, you actually need to figure out the total pressures in the balloon. And so you're going to do the total pressures by adding all the parts together. So you're going to add the 345 to 416, get a total pressure of 761 torrs. So now you can go back and figure out the mole fraction. And so for oxygen, you just take 345 and you divide it by 761. And for nitrogen, you take 416 and you divide those by 761. You take the parts and you divide it by the whole, you get 0.453 of oxygen and 0.547 of nitrogen. So for number 21, it gives me a little bit of data. It tells me I have a container. It has 0.34 moles of chlorine gas in it. And the same container also has 0.22 moles of xenon gas and 0.56 moles of krypton. And so then it tells me the total pressure is 1.1 atmosphere, and I am trying to find the partial pressure. So this one is a little bit similar to the last problem. They're just asking for it a little bit differently. Since I want to know how many total moles there are in here, so if you will go through and you will add up all the moles, go through and add up 0.34, 0.22, and 0.56, you should get a total mole count of 1.12. So now I'm going to go through and I'm going to use this information to find the mole fraction. And so let's do it for chlorine. So for chlorine, you're going to use 0.34 and you're going to divide it by 1.12 because we're trying to find the fraction of that is chlorine. And we're going to get 0.3 is the mole fraction of chlorine. So we're going to do it also for xenon. I hope you can see my marker. When you do 0.22 divided by 1.2, you get 0.20. And then the next one, I'm actually going to come up here for space sake, and we're going to find X for krypton, which is 0.56 divided by 1.12. So this is the X for krypton. This is the it for chlorine, and this is it for xenon. All right, so I have basically found the mole fractions of all the parts of this equation, and now I'm going to go back and see, it wants to know the partial pressures of this. And so the pressure, I know now this is basically, look at this like a percent, and so this is like 50% krypton, 30% chlorine, and like 20% xenon. And so it's the same for pressures. And so if there's a total pressure of 1.1, I can figure out the partial pressures by just taking this number and multiplying it by 1.1. And so this will give me basically what half of 1.1 is. And you get 0.55 atmospheres. So go ahead and do the same thing for this one. Multiply this one by 1.1 and it will tell you the partial pressure. So that one felt a little bit confusing. So just to recap, I am given, above my math here, the number of moles of everything in my vessel. And so let's say I have a balloon and in it you have chlorine, xenon, and krypton. And it wants me to know what the pressure of each of those gas in the balloon is. And so I first am gonna figure out, they call it the mole fraction, but it's kind of like a percentage of each of those gases in the balloon. And so I take that there's 1.12 moles in the balloon, and so I take the number of moles divided by the whole to get the fraction of it. And then once I know that this mole is 0.5 or 50%, I also then know that the whole balloon has 1.1 pressure, and so all the partial pressures added up equal 1.1. Well, this one is half of that 1.1, or 0.5. So I take 0.5 times 1.1. Now I can check myself if I went through and I added up 0.55 times 0.55 plus 0.33 atmospheres plus 0.22 atmospheres, I should get the total pressure of 1.1 atmospheres. I'm glad we're almost done. We have 2 left because my board's really dirty, it's getting dark, and my marker's basically done. But number 22 tells you a camper boils some water to cook dinner. They're cooking the same dinner 2 nights in a row. But one time it takes longer for the same amount of the same dinner to cook on the second night. And so compare the pressure of your experiences for the 2 nights. So basically you're cooking dinner and one night it takes longer. And so it wants to know is which night had the lower or the higher pressure. So if you'll remember, as the air pressure changes, it affects the temperature at which water boils. Well, on the second night, it took the food longer to cook. So I can assume that the water boiled at a lower temperature. The water is not getting as hot, and so the food is taking longer to cook. And it actually takes, the water will boil at a lower temperature when you have a lower atmospheric pressure. So the second night, the pressure was lower, so the water boiled lower, and so the water couldn't get as hot, so it took longer to make dinner. For the very last problem of this, they're actually giving you a lot of steps and a lot of equations, but they basically tell you you're making some magnesium bromide using this beautiful equation. And so you're taking magnesium, we're mixing it with hydrobromic acid, and we're gonna get magnesium bromide and hydrogen gas. Now this is a reaction that's done over water, and you actually do what we call collecting it over water. You may do this in lab. It's kind of a hard concept to explain, but what we're doing here is when we collect this over water, she's actually collecting 3.41 liters of hydrogen gas. So they give me the information of hydrogen gas. Is that 3.41 liters? They're also telling me that it happens at 0.981 atmospheres and it's at 60 degrees Celsius. So they give me a lot of information about that hydrogen gas there. Then I am asked, how many moles of gas did you make? And so it tells you can actually use a table on page 311 of your textbook to help you with this problem. And so naturally I'm looking for moles, so I know I want to use the ideal gas law. So I need, let's see if we have everything for it. Pressure, got that. Volume, have that. Moles, yes. R, yes. And temperature. Now, when I think about the pressure that I have here, I cannot use the gas law immediately because I want to solve this gas law for hydrogen and for the hydrogen gas only. And I'm told this is actually collected over water. And so if it's over water, I know that in that gas is water vapor. And so this is a really hard problem, so try to stick with me through this, okay? So I am going to first take the partial pressures law, and I'm going to use that to figure out just the pressure of hydrogen. And so that's why it tells you to use a chart in your book on page 311. You go to page 311 of your textbook, you can figure out the pressure of water in the 60 degrees Celsius scenario that they give it to you. And it tells you that it's at 149.4 torrs. Unfortunately, we don't use torrs for the ideal gas law, but we'll start with it. So it's at 149.4 torrs. I'm going to calculate that to atmosphere. 1 atmosphere, 760 torrs. So if I have 149.4 torrs, and I'm going to divide that by 760 torrs so that I get it in atmosphere. You're probably hearing my dog sneezing in the background. Sorry about that. And so that tells me that the pressure of the water that it's collected over is 0.1966. Now, I then know that if I'm using my pressure law, the total pressure is going to be all these pressures added up. So I've got 0.1966. And I don't know the pressure of hydrogen gas, but I do know the total pressure, which is 0.981. So I can then do basic subtraction and calculate that the total pressure of the hydrogen gas is 0.784 atmospheres. So I'm not going to use 0.981. I'm going to use 0.784. Let me erase this. Pretty much now for everything else, I need to make sure that everything else is in the right unit to calculate through. And so we have pressure in atmosphere. We are looking, do we have volume is in liters? We are looking for moles. And of course, temperature is in Celsius, not in Kelvin. So let's take 60 degrees Celsius. Add 273.5. What do you get? 333.2. So I'm just going to go ahead and take this guy here. PV nRT. All right, pressure. We figured out 0.784. Volume 3.41. I'm looking for N. I know O. I know R. My marker is dead. And then temperature, which is 332 kelvins. I know that it's getting hard to see, and I'm really sorry for that. So if you take all that and you solve it through for moles, you get an N of 0.0977 moles. So just to recap what I did, they didn't give, this is a problem where I'm collecting a gas over water. And so since it's over water, I also have some vapor pressure of water in my sample. And so I had to figure out from a chart in the book what the pressure of water was so that I could use Dalton's law of partial pressures to subtract that from the pressure they gave me of the total gas. Found the pressure of the gas, made sure every unit was in the right unit for the ideal gas law, and then solved for moles. All right, great job. You're done with the chapter 10 review questions.